Dear students, today we will discuss about rank nullity theorem. Statement of rank nullity theorem is if transformation T from U to V, here U is a finite dimensional vector space, V is another dimensional vector space, be a linear transformation of U is a finite dimensional vector space, and then dimension of R of T, here R of T is range of T. Range space, here R of T is range space, dimension of R of T plus dimension of N of T. N of T means null space, which is nothing but which is equals to dimension of R of T and dimension of N of T, which is equal to dimension of the U. U is domain here. Dimension of U, which is rank nullity theorem, statement of rank nullity theorem, which is also called as rank. Rank is nothing but dimension of range space and dimension of null space, which is nothing but nullity. Dimension of null space, which is nothing but nullity, which is equal to dimension of domain. Here domain is U, finite dimensional vector space. Okay, we will solve one problem on this rank nullity theorem. We will solve this problem. The problem is that T from, this is transformation, linear transformation, T from U to V, a linear transformation defined by T of x comma y comma z, which is equals to x plus y comma x minus y comma 2x plus z. X comma y comma z belongs to R. R is vector space here. Find the range, null space, rank, nullity, and hence verify rank nullity theorem. First, here bases are not given, so we take standard basis. Standard is this is in the three-dimensional vector space and RHS also in three-dimensional vector space. Therefore, we take standard basis of order 3. Order 3 means three-dimensional standard basis. Standard basis are E1 1, 0, 0. E2, this second standard basis 0, 1, 0, and E3 0, 0, 1. These three are standard basis in three-dimensional vector space. First, we have to find, substitute in place of x, y, z. We get T of 1, 0, 0. Which is equals to, apply in this linear transformation, we get T of 1, 0, 0, T of x, y, z. Here x plus y, here x is 1, y is 0, z is 0. Therefore x plus y means x plus 0, x is 1, comma x minus y means 1 minus 0, gives 1, comma 2 into x plus z, 2 into 1, 2 plus z is 0. We call this as alpha 1. And T of second standard basis 0, 1, 0 is equals to, here in place of x we have 0 and in place of z we have 0, but in place of y we have 1 here. Therefore substitute in place of y 1, we get x plus y means 0 plus 1 gives 1, comma x minus y, 0 minus y gives minus 1, comma 2 into x plus z gives 2 into x. There is no y term, therefore which is equals to 0. We call that as alpha 2. T of third standard basis 0, 0, 1, 0, 0, 1 is equals to, substitute in place of z 1 and in place of x and y 0. X plus y gives 0 plus 0 gives 0, and x minus y 0 minus 0 gives 0, and 2 into x plus z. Here x is 0, therefore only z term is 1, which is equals to alpha 3. Okay. From this we write matrix of linear transformation. Matrix of using this linear transformation, using these vectors, we write a matrix A as We find determinant of this matrix. Determinant of A is 1 into minus 1 into 1 minus 0 into 0. Minus 1 minus 0. Then minus 1 into 1 into 1 0, minus 0 into 0. Minus 1 into 1 minus 0 plus 2 into 0 minus 0. 2 into 0 minus 0 gives 1 into minus 1 and minus 1 into 1 minus 1 and this term becomes 0. Therefore minus 2. Determinant of A is minus 2. Therefore determinant value is not equal to 0. Therefore the given these three are linearly independent, which is not equal to 0. Therefore linearly independent. Since the matrix is linearly independent, therefore images forms the basis of RT. Since this is linearly independent, therefore images forms the basis of R of T. Let images are here 1, 2, 3, alpha 1, alpha 2, alpha 3. Alpha 1, alpha 2, alpha 3 forms. These three are linearly independent. Alpha 1, alpha 2, alpha 3 are linearly independent. Therefore, alpha 1, alpha 2, alpha 3 forms basis. Okay, alpha 1, alpha 2, alpha 3 forms basis. Therefore, alpha 1, alpha 2, alpha 3 here. The rank of this matrix is, by using this linearly independent and alpha 1, alpha 2, alpha 3 forms basis means rank of this matrix is 3. Rank is 3. Okay, rank is nothing but dimension of range space R of T, which is equals to 3, which is same as dimension of R of T. Okay, rank is 3. Next, we have to find range. Find range. To find range, let alpha belongs to range space of T. Then alpha equals linear transformation of T of x into T of E1. T of E1 is T linear transformation with standard basis. X into T of E1 plus y into T of E2 plus z into T of E3. Here x into T of E1 is nothing but alpha 1 plus y into T of E2 is alpha 2 plus z into T of E3 is z into alpha 3. Here alpha 1 is x into alpha 1 is 1 comma 1 comma 1 1 comma 1 comma 2 plus y into alpha 2 is 1 comma 1 comma 0 1 comma minus 1 comma 0 and alpha 3 is 0 comma 0 comma 1, which implies we get x and y z. X plus y plus 0. X plus y 0 term is not there here. X into 1 is x, y into 1 is 1, y into minus 1 is minus y, x minus y plus 0, z term is 0, comma x into 2 2x plus y into 0, 0 term is 0 here, y term is 0 here, 2x plus z into 1 is z, 2x plus z, given x comma y comma z belongs to R. This is range of T. Okay. Next, we will find null space. Null space, if x comma y comma z belongs to n of t, then t of x comma y comma z which is equals to 0. Null space is, the definition says t of x comma y comma z which is equals to 0 provided x comma y comma z belongs to n of t. Then t of x comma y comma z means x plus y comma x minus y comma 2x plus z, x plus y comma x minus y comma 2x plus z. 0 means 0 comma 0 comma 0 here in RHS. X plus y equate corresponding elements, we get x plus y is equal to 0 and x minus y is equal to 0 and 2x plus z which is equals to 0, which gives the null space n of t as x plus y is equal to 0, x minus y is equal to 0. By this, x equals y. Then if we take x as 0, then we get y is 0. Then 2x plus z, 2x plus z, we substitute in place of x 0, then we get z as 0, z equals 0. Therefore, null space is 0 comma 0 comma 0. Dimension of null space is 0. Dimension of null space is 0. Therefore, we get dimension of null space, which is nothing but nullity. Dimension of null space is nothing but nullity. Rank nullity theorem says, it states that dimension of range space R of t plus dimension of null space n of t which is equals to dimension of u. Here dimension of u is 3-dimensional, u to v. This is 3-dimensional vector space. Therefore, dimension of R of t is, rank is 3 here. Therefore, 3 plus dimension of null space is 0, which equals to 3. Dimension of u is 3. Therefore, 3 equals 3 means rank nullity theorem is verified. Understood? This is problem. We will solve one more problem on rank nullity theorem. The problem is, find the range, null space, rank and nullity, and verify rank nullity theorem for the transformation T from V3 of R, the 3-dimensional vector space, to V2 of R, 2-dimensional vector space, defined by the transformation is, linear transformation is T of x comma y comma z equals y minus x comma y minus z, provided x comma y comma z belongs to R. Okay, first we have to, here basis is not given, basis are not given. Therefore, we will take standard basis of 3-dimensional vector space. Standard basis E1 is 1 comma 0 comma 0 and E2 is 0 comma 1 comma 0 and E3 is 0 comma 0 comma 1. These are all standard basis in three-dimensional vector space. The transformation of this using this basis we get t of 1 comma 0 comma 0 which is equals to, substitute in place of x 1, y 0 and z 0. We get, substitute y minus x gives y minus x, y 0 minus 1 gives minus 1 comma y minus z, y minus z. Here y is 0 and z is 0, therefore which gives 0. We name this as equation 1, and t of 0 comma 1 comma 0 which equals, in place of x substitute 0, in place of y substitute 1 and z, in place of z substitute 0, we get x minus y. Here y is 1, y minus x, y minus x, 1 minus 0 gives 1 comma y minus z, 1 minus z is also 0, therefore 1 minus 0 gives 1. We call this as alpha 2, and t of 0 comma 0 comma 1, so you can substitute in place of x and y 0 and in place of z substitute 1. We get y minus x, 0 minus 0 gives 0 comma y minus z, y 0 minus 1 gives minus 1. Call this as alpha 3. By using this, we write matrix of linear transformation, that is A equals minus 1 0 1 1 and 0 minus 1. This is matrix of linear transformation. To find rank, we use row radius echelon form to find rank. Okay? For that, we interchanging here R row 1 interchange with row 2. We get 1 1 minus 1 0 0 minus 1. Okay. This is non-zero leading entry in the first row, therefore this becomes pivot of first row. Then below that elements we make 0. To that we have operation called R2. We are doing for R2 plus R1, R2 dash, R2 plus R1, and R3. In R3 this is 0, therefore nothing to do. 1 minus and 1 plus R2 plus R1. R2 is minus 1 plus 1 gives 0 here, and 0 R2 is 0 plus 1 gives 1, and 0 minus 1. Then we use R3 dash equals R3 plus R2. Then we get 1 1 0 1 and 0 plus 0 0, and 1 plus minus 1 gives 0. Therefore, the number of non-zero rows in this matrix is 1 2. This is 0 row. Therefore, the rank is 2. Number of non-zero rows becomes rank. Rank is nothing but dimension of the range space. Dimension of the range space is, which is nothing but rank, which is equals to 2. Next, we have to find the range. We have to find the range. To find range, alpha belongs to R of t. Then alpha equals x into t of E1. Here these two forms basis. Here spanned by this subspace, spanned by the vector subspace. spanned by 1 comma 1 and 0 comma 1. These two forms basis. Therefore, by using this, x into 1 comma 1 plus y into 0 comma 1. These two are the base. These two forms basis. Then we get x plus y comma x here. X plus y is 0. X comma x plus y. X plus y. Here x comma y comma z. X y belongs to V2 of R. This is range R of t. R of t is x comma x plus y. This is range R of t. Dimension of range of t is rank, nothing but rank, which is 2. Next we have to find the nullity. Null space, then nullity. So null space is, to find null space, we take x comma y comma z belongs to n of t. Means t of x comma y comma z, which is equals to 0. Null space means t of x comma y comma z belongs to 0, provided x comma y comma z belongs to n of t. T of x comma y comma z, which is equals to 0, means the linear transformation given y minus x comma y minus z. Y minus x comma y minus z, which is equals to 0 comma 0. Y minus x, which is equals to 0, which gives y equals x, and y minus z, which is equals to 0, which implies y equals z. If we take, let x as k, some scalar k, if we take x as k, then y is also equal to k and z is also equal to k. Therefore, null space is n of t is k comma k comma k. X comma y comma z, which is equals to k comma k comma k, which is nothing but, in particular, k is not 0. In particular, we take 1 comma 1 comma 1. Therefore, we get null space as 1 comma 1 comma 1. Therefore, dimension of this null space is dimension of n of t, which is equals to 1 comma 1 comma 1, which is nothing but dimension of null space is nullity of, which is nothing but nullity. Therefore, we got nullity and rank. Then verify rank nullity theorem. Rank nullity theorem states that R of t, rank, which is nothing but dimension of range space, plus n of t, which is nullity, which is nothing but dimension of null space, which is equals to dimension of this one, V3 of R, dimension of domain. Rank is 2 here. Null space, nullity is, dimension of the null space is 1. 2 plus 1, which is equal to dimension of the domain. Domain is V3 of R. This is in 3-dimensional vector space. Therefore, 3. 2 plus 3. 3 equals 3. Therefore, rank nullity theorem is verified.